Okay, so I want to look at some more examples with parametrics. And remember from the first video, we talked about parametrics meaning that it just adds a parameter. And a lot of times that parameter is time. Like it gives us an idea of when is it at a particular point, when is it, at a particular location, if you're describing the path of a particle. Okay. And so I want to kind of almost go backwards in a way of saying, okay, here's some information. So example 3, I have some data in terms of like locations, and even example 4, I see the path and I have some times. I want to create parametric equations that not only model the position, but also how fast that it's going through that. Okay. So like the kinds of paths that we're going to do are going to be very basic, quote unquote, lines and parabolas, circles, ellipses, things like that. Okay, so right away I know and I see it's a line segment. Okay, so when you know that the path is a line segment, that means both the x and the y component will be linear with respect to time. So if you wanted to even like sketch out like a little graph here saying, okay, a line segment begins, so time equals 0 at the point 3, 8. So at 3, 8, that's where we're at 0. And ends 30 seconds later at -2, 20. So like 3, 8, and then -2, 20, which is like way up here. -2, 20. And that's when t equals 30 seconds. So because it's linear, right, I know that the x position and the y position must change, in a linear relationship over time. So over 30 seconds, let's do the x one first. Over 30 seconds have to elapse, and the x has to go from 3 to -2. So like my x has to decrease by 5 over 30 seconds of time. And so I could think about that as almost like a -5 over 30, like the change in x over the change in time. So like basically it's like a -1/6 ratio. And I'll call this x. Okay, so that ratio, that slope, so to speak, is the change in time, the change in x over time, and the initial point when time is 0 was 3. So I'm going to create this linear function, and x equals -5 over 30t plus 3, and you could reduce that to like just x equals -1/6 t plus 3. Now we only have 2 data points, but we could put those 2 data points in and see. So if I put in time equals 0, well, that goes away, and I just get 3, which I knew. And at time equals 30 seconds, -1/6 of 30 is -5, and -5 plus 3 is -2. So here represents the linear function for x. Okay, now y, it'll be very similar. Now the y change, maybe I'll go a different color here. I'll go this gray. Y changed from 8 up to 20. So it increased by 12. So it increased by 12. Okay, there you go. Over the 30-second time. And then at time equals 0, its initial point was 8. So 12/30ths, both divisible by 6. So that's like 2/5. So y equals 2/5 t plus 8. And again, we could check our data point. Let's put in 30 seconds. 5 into 36, 6 times 2 is 12. 12 plus 8 is 20. Okay, so this would represent the path going in that linear direction, starting, here and ending up here, and it's going to take it 30 seconds. Now, let's say you want to go faster, right? It says find the parametric equations that only takes 10 seconds. So we're not changing geographic location, we're just getting there faster. And so that's going to affect the slope, right? Or the rate that the x changes over time, and the rate that the y changes over time. So now when I go back and write these equations, let's go squared. So now my x is still decreasing by 5, but it's only going to take 10 seconds for it to decrease. I'm still starting at 3. So the x would be negative 1/2 t plus 3. And then the y is still increasing by 12, but it takes only 10 seconds to increase. And we're still starting at 8. So then y is equal to 6. So y equals 6/5 t plus 8. And again, together we need those in terms of the parameter. And if you put in, let's say 10 seconds, to each of these respectively, we should get the position -2, 20. Okay, so linear functions aren't too bad. Now, when we're going to get functions that are parabolic, there's going to be one assumption to this. And the assumption is that one of the variables will change in a linear fashion, whether that's the x or the y. And so, and it's easy to tell which one it is, but we have to make that assumption that, okay, one of them will change at a constant rate. Okay, so if I look here at time equals 0, and I'm moving up here, if I think about the different components, if I think about, let's say the x component, the x decreases, right? Because we're going from 3 to 2, then the x increases back to 3, and then the x increases. In other words, since this parabola is opening sideways, the x variable is going in both directions. It's first it moves up to the left, then it moves to the right. Okay, so that is going to represent the quadratic portion of this parameter, because it's the x that sort of double backs on itself. Okay, if the parabola were open up and down, then the y component or the y variable would have the parabola or the quadratic function. So since I know in this example x has it, I'm going to then assume y is changing in a linear fashion. And take a look at your y value: -6, -2, +2, 14. So the y values at every instant are increasing. Okay, so let's think about what that rate of increase is. So it takes 2 seconds, and the y increases by 4. It takes 2 more seconds, the y increases by 4. It takes 6 seconds, right, from time equals 4 to time equals 10, and the y increased by 12. So whether you're thinking of it as 12 over 6, or you're thinking of it as 4 over 2, the ratio for the y component is a 2-to-1 ratio. And at time equals 0, the initial y value is -6. So the y is easy to get compared, I think, to the x. So y equals a slope of 2t minus 6. And again, if you're not sure if that's the correct one, put in a data point. Let's say we put in time equals 10. If I put 10 into the time, 2 times 10 is 20, 20 minus 6 is 14, and that is the correct y value. So when you have a parabola, you're analyzing the path of a parabola. Figure out which way it's opening, by looking. And then, so if this is opening in an x direction, that means the other variable, the y, would be the linear variable, because it's the x that's going to be quadratic. Okay, now, so now that we know the x is quadratic, we're going to put it into vertex form. And so, and be really careful, because our vertex is going to be x in terms of t. So, if I think about vertex form, x equals some coefficient a, t minus, I guess, h squared plus k. So this is vertex form. A, remember, determines how wide does this open. The variable is t, so our vertex is h comma k. So if our vertex is h comma k, but we have to remember, and this is where it gets confusing, h, because it's part of this component, h is actually a t variable, And k, because it's outside, is actually an x variable. And that's what gets sort of confusing, because usually it's like y in terms of x. This is x in terms of t. So in this case, x is serving as the dependent variable. It depends on the parameter of time. Okay, now here's our vertex, right? Let's go with this nice blue color here. This right here is our vertex. So I have to identify the time value is 2, and the x value is also 2. And so I've got to be really careful. I guess this wasn't the best example. Okay, Mr. Brown, note for next year, a better example. But this time equals 2. Time equals 2 is going to go there, where the x component of 2 is going to go here. Okay, so, and then we've got to solve for a. How wide is this opening? And that goes back to the rate. So I'll go back to my pen. So I know x is equal to a t minus 2 squared plus 2. And in order to solve for how fast that's opening, you pick any other data point. So you can pick 0, you can pick 4, you can pick 10. So I would say let's pick 10. So at time equals 10, so 10 minus 2 squared plus 2, the x value at time equals 10 is 18. So 18 equals a times 10 minus 2 squared plus 2. So 18 is equal to a. Well, 10 minus 2 is 8, and 8 squared is 64 plus 2. So I can subtract the 2 over. So 16 equals 64a divided by 64. So my a value is 1/4. And I would have gotten that no matter what I picked. Okay, so now I know what my x component is. X is equal to 1/4 quantity t minus 2 squared plus 2. And again, let's check another data point. Let's just put in 0 just to make sure that works. Do we get a value of 3? 0 minus 2 is -2. -2 squared is 4. 1/4 of 4 is 1. 1 plus 2 is 3. So here are the parametric equations for this particular path. Okay, again, try some practice examples on the homework, and then the next video, we'll take a look at ellipses and circles and just a little bit in terms of hyperbolas.